Hello. In the last few lectures, we were discussing about the different mapping schemes, direct mapping, set associative mapping, and fully associative mapping, right? So, in that, what were we talking about? We were talking about in what set or in what location in the cache memory do we have to copy a data from the main memory, right? Where in the cache memory we were to write or copy a new data from the main memory. So, in direct mapping, whenever there was a new data and a new block to be copied from the main memory, and if there was another data sitting in the location in the set where this new data was supposed to be copied, then there was no hesitation, the older one was evicted, it was replaced. But there was no doubt in that, because anyway it has to be evicted, only one block was there in each set, so there was no doubt there. But when it comes to set associative mapping and fully associative mapping, the problem is that there is multiple choices, because in each set there are n number of blocks, right? And we should decide, or the processor or the designer should decide, which of these blocks have to be replaced by the new one. This this policy regarding which one will be replaced, and there should be some uniformity regarding this, right? So this policy is called as a replacement policy. So replacement policy decides in set associative mapping and fully associative mapping which block has to be replaced when a set is full. That is the concept of replacement policy. And one of the most widely used replacement policy is the least recently used, or LRU. Okay. It is very much self-explanatory. The idea is that what is the idea? The idea is that the data or block of memory being used at the latest point, it will be, or the most recently being used, it might be used again in the near future. This was the concept of temporal locality, right? So least recently used, right, replacement policy is aiming to exploit this concept of temporal locality. So now that is, since now that is fixed, that is decided, we will be using the least recently used. We need to know how to identify the least recently used block, right? Because without identifying the least recently used block, we cannot replace that. So for that we are using this use bit denoted by U. So the idea of use bit is that use bit will determine, or it will denote, which of the blocks in the memory is the least recently, which of the blocks in the set, which is the blocks in the set is the least recently used, and that can be replaced. So we will see an example to make things clear. So consider this example. We have three load word instructions, and we have to copy it into the cache. So if you convert these into binary, all these three will come into set 1, and here we are using an 8-word cache, which is two-way set associative. That is, each set will have 2 blocks. Okay, and block size is 1 word only. So this is the same cache memory that we have used in the earlier things. So the value of U will denote which is the least recently used block. That is the idea. Now during the first time, what happens? First we will copy the content from 0 4 and we will copy it into this block, right, in set 1. Then we will go here and take this content from this memory and copy it here in this block. So now what should be the value of u, that is use bit? It should be denoting block 0, right, because this is the this was used, then this was used. The most recently used one is this one, and this is the least recently used, right. So value is 0. Now what is happening? Now we have to copy this one, 54. The content of 54, where will it be stored? It will be stored in this block, right. And what will be the value of u then? Use bit, it will change from 0 to 1, because when 54 comes here, 54 is the most recently used and this 24 is the least recently used. So this u should change to 1. So that is what is happening here. We copied 54 here instead of 4, because at this point this was the least recently used and we copied it here, and now we changed the use bit to 1 to denote that this block is the least recently used. Now if there is another replacement is coming, then this one will be replaced, right. So that is the idea of a least recently used replacement policy. So there is something else known as a pseudo LRU. The problem with use bit is that as the number of blocks per set increases, we will need to increase the number of use bit also, and this is an overhead which from a design point of view is something that we try to avoid. So for that, what we do is we divide the whole number of blocks into certain groups, right. Certain group means, so each group will have some number of blocks. So total number of groups will be less than the total number of blocks. So to denote a certain group, we don't need as many use bits as we would have needed to denote the number of blocks. So here we are reducing the number of use bits. We are using use bits, but we are reducing its number. And what we do, once we identify the least recently used group, from within that we randomly delete one block. Within that there is no logic. Some random block will be evicted from the least recently used group. That is called as pseudo LRU. There is another thing, another replacement algorithm or replacement policy known as FIFO, first in first out. In that, it is the eviction is not based on the recentness of the use. It is based on the which one was copied into the cache memory first, or the oldest one, first in first out, like a queue. But LRU and pseudo LRU are the ones being used in practice in most of the computers. Okay, now coming to the last topic in our cache memory, which is write policy. See, till now we were discussing regarding which data has to be or from to which location data from the main memory had to be copied into the cache. All of this was regarding read operations, right? Whenever the processor wanted to load something into the cache for accessing. But there is also a condition when there is a write also, right? Because this is a MIPS processor or any processor, there will be some memory write. In the particular case of MIPS processor, it is a load store processor. That is, the data to be manipulated is loaded into the processor, it is manipulated and it is stored back. So like we are reading something from the cache, data is always from the processor's point of view, it is written into the cache only, and from the cache it is written back to the memory, main memory. So that is the question here. Write policy means when and at what point of time or how frequently we update the main memory when the corresponding memory in the cache is updated by the processor. For that, there are two policies. The first one being a write through, second one being write back. So in write through policy, what we do is, whenever there is a change in data in the cache memory, the corresponding memory block in the main memory will be updated. So I am repeating once more, whenever a block in the cache memory is updated, the corresponding block in the main memory is updated every time, each and every time. In write back, what is done is, whenever a cache block is evicted, if it is updated, then the corresponding block in the main memory is updated, right? So once more, whenever in write back policy, whenever a cache block is evicted, if it has been updated by the processor, the corresponding main memory will be updated, and whether a block has been updated or not is denoted using dirty bit. Okay, the concept of dirty bit, like valid bit and use bit, we just add one more bit called as dirty bit. So comparing these two, write through and write back, so what are the differences? In write through, we don't need an extra bit, right? We don't need an extra bit. But the problem with write through is that there is a whole lot more of data memory writes, because every time the cache memory is updated, we have to update the main memory also, and updating main memory is a slow process. So it is sort of a waste of time. And the problem with write back is that it requires another extra bit, which is a dirty bit. But in most computers, modern processors, we are using the write back policy, because from the point of view of efficiency of time management, time efficiency, this is better. So most processors we are using write back policy, right? So this is we are concluding the lectures on cache memory, and the only topic remaining is virtual memory, which we will cover in the next 3 or 4 lectures. Thank you.